Okay, so last time we talked about how to find series solution near ordinary point. That was 5.2, and just to revisit all of this, we assume that the solution form is the infinite sum power series a(n) x to the n, and you can write out some of the terms, a0 plus a1 x plus a2 x squared plus a3 and so on, right? And then the idea is to find what are these coefficients, a0, a1, a2, a3, and so on. Can you find these coefficients? The answer is yes. If we have a recurrence relation, we can find these coefficients, plug them in, and that will be our series solution to the given particular differential equations. And then you can also apply initial conditions. So we did this problem, but that was very short, not much. But we took the long way, and then we show that the solution is just simply sine and cosine multiplied by constant a0 and a1. And then we started working on this problem last time. This was one of the questions from past final. And this was a pretty long question. So we did almost all the work for this problem last time, but we didn't really get to find the coefficients. So we did all of this. You can find this in our previous notes, and we got to the recurrence relation, or recursive formula if you want to call it. So this is where we're going to start today. So I copied the recurrence relation here so that we don't have to keep going back and forth. So this is from last time. So again, let me know if you guys have questions and speak through your audio that way. It's better. It's better for me, better for you. I get to know you, I get to hear your voice, so why not, right? So we have this differential equation. We want to compute the recursive formula. We have it right here for the coefficients. So let's compute some coefficient using using these initial conditions. So we're given two initial conditions, one on the derivative and the other one is on y of 0. So let's see, how do you use initial conditions? So we know that the solution to this equation, it's going to be y equals a0 plus a1 x plus a2 x squared plus a3 x cubed and so on, right? In closed form, we say this is the infinite sum. So I'm ignoring the indexing, and I show you guys it's okay for this course. So ignoring them for now, a(n) x to the n. That's the closed form for this expanded infinite sum. Now, how do you use the initial conditions? Well, where do you apply y of 0 equal -6? Well, you apply that to the solution you just came with, right? So y of 0 equals -6. Well, that means you're plugging in 0 for everywhere you see x. So if I plug in 0 for this x, and this x, what do we get? We have -6 is equal to a0. Because all the other terms, they will just disappear because they're all 0. And then what about the second condition? Where do you apply the second condition? Good. So if we compute the derivative of our solution, we have y equals, a0 goes to 0 because that's a constant, a1 plus 2a2 x plus 3a3 x squared and so on, right? And now if I sub in my initial condition, y prime of 0 is equal to 2, so we plug in x equals 0. Now if I plug in x equals 0 here, and for the remaining terms, they will all carry an x. So they all disappear. So we have the condition that 2 happens to be a1. So that's why we can kind of generalize that if you have an initial condition, we know that the first condition is always A0, and you see why, and the second condition is always A1. If I give you another one, which will be on the second derivative, and you will know that will be A2, and so on. So you see why these conditions, they're just automatically can plug in A0 equals to the first condition, A1 is equal to the second condition, okay? Hopefully that makes sense. So now that we have our A0 and A1 figured out, let's find what are these coefficients. So we know A0 and A1. What about A2? We're going to compute A2 from the recurrence relation we computed last time. So let's do that. So using the recurrence, we're going to compute, let's see, how many non-zero terms does this question wants. We want first 4 non-zero terms. So we already have 2 of them. We have A0, A1, so we need to go for 2 more. So using the recurrence, so if n, well k in this case, if k is equal to 0, we have, so I'm going to use the recurrence relation. What do we have? We plug in k equals 0. Just make it smaller so I can see the recurrence. So if k is equal to 0, the first term will go to 0. And then the second term will also be 0. Third term is minus a sub 0 over 3 times 2 times 1. So A2 is just negative A0 over 3 times 2 times 1, that's 6. Well, since we know the value for A0 because it's an initial value problem, we can substitute what A0 is. But if we didn't have that, you'll leave it as A0, just like we did last time. So I'm going to sub in what A0 is, that's negative 6. So we have 6 over 6, that's 1. So A2 is going to be 1. So we have 3 non-zero terms. We're going to go for one more. K equals 1. So I'm going to have A sub 3. So let's plug in k equals 1. So we have 1 times 2 times A sub k is 1. So that's going to be A sub 2 minus, for the second term on top, we have 1 times A sub 1 minus 1, that's 0, minus A sub 1. Everything over 3 times 2. So that's for A sub 3. And by simplifying this, we have 2A2 minus A0 minus A1 over 9 times 2, that's 18. And then I'm going to sub in what these coefficients are because we know them. We know A2 is 1. We solved previously. A0 is negative 6. So negative, negative, that's positive 6. And A1 is 2, so that's minus 2 all over 18. And what does come up to be, guys? Let's check this out. 7 over 18? No. 6. Okay. Alright, so that's 1/3. Whew, we know how to add. Okay, good. That's common, right? When you see a lot of numbers flowing around, you just kind of put them in different bays, so they work out nice. Alright, so we have 4 non-zero terms. Successful. Let's write out the solution. So our solution to this problem is going to be y equals a0 plus a1x plus a2x squared plus a3x cubed, and of course there's more. We don't want them, we just want 4. First 4 non-zero. So our solution is going to be negative 6 plus 2x plus a2 we found it to be 1, so that's just x squared, and plus 1/3 x cubed, and of course there's more. So that would be our series solution to this. So it's kind of nice, right? Not so bad. It's a nice polynomial. So any questions on this problem, guys? Does it make sense? Uh-huh. Mm-hmm. Then they don't count. You have to keep going until you find non-zero term. Yeah. So so we write out the solution a0 plus a1x plus a2x and so on, right? So if, say, a3 happens to be 0, if this was a 0, then this would disappear. So we don't have the 4 non-zero terms. So we have to go for the next term, a4 plus x to the 4, a4 times, right? So you have to write out the first non-zero term, as many terms they want. So in this case, 4, so we found all 4. Okay, yeah. All right, so that's that. Any other questions on this problem? So this was a good long problem, but at least we got to practice with this question, so that was a success. So let me do another question on series solution, so that way we practice at least 3 problems together. So we did 2 so far. So the next problem, I copied it right here. This is from the textbook. So I'm just gonna put it on the same document. So here's the direction for the next problem. And let me just copy the question. So this one has less terms, so it's not that crazy like the previous one. But the idea is the same. Even if you have more terms, you're still following the same procedure. All right, so let's call this example 2. So we want to seek power series solution of the given differential equation about the point x0. X0 is 0, so in our class, x0 is always going to be 0. Unless you're doing a homework question, then x0 is probably not 0. But that's okay. Homework you do a little heavier. So it's okay, because you're home, you're doing extra practice. And then once we find the recurrence relation, we're going to compute the first 4. I'm going to cut down to 3, okay? So once you have the recurrence, you have the idea of getting the coefficients. So just cut it down to 3, so we save time of the 2 solutions, y1 and y2. All right, so let's see. So we are assuming that the solution is a series solution centered at x0 equals 0. So y is equal to the sum, again, ignoring the indexing, an times x to the n. That means y prime is going to be the expression, the sum, n times an x to the n minus 1, and y double prime is going to be the sum, n times n minus 1, an x to the n minus 2. Okay, now let's plug these into our expression. Now if my differential equation involves more than one term in front of any of these terms involving y, I like to distribute so that it looks a little simpler. So we have the following. We have 1 times y double prime minus x times y double prime plus y equals to 0. And now I can plug in the expression for y double prime in terms of summation. So let's do that. So we have the second derivative that's going to be the sum, n times n minus 1, an x to the n minus 2, minus x times the sum, n times n minus 1, a sub n x to the n minus 2, plus y is our assumption, so y sum an x to the n equals to 0. Plugging it in, okay? Let me know if you guys have questions, or else I'm just gonna keep going. Okay, so let me know if you guys have questions. Well, now we do that a little shifting, right? So in order for me to do that, I just come up with a substitution again. So I'm gonna let k b equals 2n minus 2. So I'm translating the entire summation into k variable instead of n. So then n is going to be k plus 2. That's for the first one. The second one, we're also going to do the same thing, right? So this will work for both. And then the last one, we'll just do k equals n. So not so bad. Okay, so after I have done that, we have the following. So we have the sum. So n is going to be k plus 2, k plus 1, so k plus 2, k plus 1, a sub k plus 2, x to the k. Oh, typo. So no one cut it. Are you guys paying attention? I made a mistake. What mistake did I make? No, that's not a mistake. That's okay. We have the second derivative twice if I distribute. Yeah. Right. I need to move this inside the summation so it combines with that one. You have to do that before you start rewriting in terms of k. So that's what I forgot. So hopefully you guys are not sleeping. K is equal to n minus 2. Well, so I'm not going to write the steps, but if I push the x inside, I have the sum n times n minus 1 an x to the what power? Yeah, right? Because you have, so here you have x to the 1, and then here you have x to the n minus 2. By laws of exponents, you're adding the powers. So negative 2 plus 1 is negative 1. Okay, so that's the only one that changes. So now I can use my substitution k for this particular summation. K is going to be n minus 1. So that means n is going to be k plus 1. Oh, okay, good. So it does change. And then this one, k is equal to n. So not so bad. Alright, so hopefully I don't have any more typo, but if I do, you guys let me know, okay? So we have the sum from ignoring the indexing. So we have k plus 2. N is going to be k plus 2. And then we have k plus 1. A sub n, that's k plus 2. X to the k. So they're all going to have x to the k. So I'm going to factor that out. Minus, and the second summation, we're going to get k plus 1 times k a sub k plus 1. Again, I'm factoring out x to the k plus a sub k. Everything gets multiplied by x to the k equals to 0. So I skipped one step, but let me know if you guys can follow me, okay? Are you guys all okay? Okay, so I'm assuming that's a yes. So now we want to solve for the higher subscript. So in this case, that will be a sub k plus 2. So I move everything to the other side, set it equal to 0. Again, I'm skipping steps. So a sub k plus 2 is going to be k times k plus 1, a sub k plus 1, minus a sub k, everything over k plus 2, k plus 1. So that's a very nice recurrence relation. See, no wonder why the textbook has a nice question. Like I said to you guys like so many times, and you probably haven't memorized that by now. So that's a really nice recurrence relation. So now that we have our recurrence relation, got it. Part B, let's find three non-zero terms, the first three. So we start with k equals 0. We get a sub 2. So remember, you want your solution in terms of a0 and a1. Only two unknown constants, because it's a second order, we only need two unknown constants. So a0 and a1, they're just hanging out by themselves. So we want everything else in terms of these two constant, the special ones. So what is A2? Let's plug in k equals 0. So the first term we're going to have a sub 0, right? Nothing. So you get 0 minus a sub 0 over 2. So that's negative a sub 0 over 2. And then when I plug in k equals 1, we have a sub what? 3. So we get k is 1, so that's 1 times 2. A sub k is equal to 1, that's 2, minus a sub 1 over 3 plus 2. 3 times 2. And then you can separate this. So we have a2 over 3 minus a1 over 6. But we know what a2 is. a2, we found that to be, so that's right here. That was negative a0 over 2. So I'm going to substitute that in there. So we have negative a0 over 6 minus a1 over 6. Okay, I think we have enough terms because we just wanted the first 3, but I went one more. That's okay. Not a big deal. So now let's write out the solutions. So y is equal to a0 plus a1 x plus a2 x squared. That's already 3, so this is good enough. So we want one extra term, but that's fine. Yeah, why don't we just write it out, right? So I'm going to go ahead and modify the question. So I changed my mind. Let's do 4. And let's write out all of them since we found them anyway. Why not? It doesn't hurt to write extra term. Okay. Now I'm going to plug in these coefficients. So we have a0, that's just a0 itself. a1 is a1 itself, plus a2. a2 is negative a0 over 2. So I'm going to rewrite that one. That's negative a0 over 2 x squared plus a3. We found that to be those guys, so that's also negative. So that's negative a0 over 6 plus a1 over 6 times x cubed, and so on. And now we kind of put them together as y1 and y2. So I'm going to group them using a0 and a1. So we have a0 times 1 minus a0. Well, I factor that out, so I don't need to write that again. So the second term is going to be 1/2 x squared. And then there's one more term, minus 1 over 6 x cubed. So it looks like I only have 3 terms. Okay. Plus a1. So now a1 has x, and then the next term with a1 it's going to be, where is the next one? That's right here. Minus 1 over 6 x cubed. So this one only has 2 terms. Okay, so I'm missing out terms, but the idea is you can get this coefficient just by plugging in maybe k equals 2, you get a sub 4, and then k equals 3, you get a sub 5, and then plug those in to your solution, you will have those terms out. But just for the time being, I'm going to stop right here for this question. It's incomplete, but because y1 and y2 doesn't have 3 terms or 4 terms this question wanted, right? So yeah, I'm just gonna put 3 like I said. So but y2 doesn't have 3 terms, so sorry for that. I should have computed one more, but I didn't, but you guys can figure that out. So you can think of it this way now. We have 2 independent solution and infinite sum. So this is y1 and this is y2. So we have 2 independent solutions because it's a second order and they're infinite. So we can't really write all of them, but we indicate them by using dot 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 notation. So any questions on this particular problem? Yep.
What does the x of 0 equals 0 stand for? Is it a, b, something?
Oh, x sub 0 equals 0. Oh, that's where we're centering the series solution. So remember, we assume that y is equal to the infinite sum an x minus x naught to the n. We're always picking this to be 0. Mm-hmm. So if you do that, then you would have to do more work from this step to the recurrence step, because you would have to write out some of the terms that we didn't consider. Mm-hmm. Right, so you will be able to, once you set that equal to 0, you will be able to solve for the highest subscript, which you can just get it from the recurrence relation. Okay, so it's okay to ignore the indexing, because when you keep track of the index, you have some initial terms that will come out by writing it out. I'm going to show that in 5.5, because 5.5 you really need to show that why do we ignore the indexing, and I think it will make more sense then. Okay, so for now we'll ignore it. Alright, so that's another solution. So again, the last part is incomplete because I don't have 3 terms, I only have 2. But if you want to go ahead and find another term, say a sub 4, you'll be able to fill that in. So I will leave that up to you. But the idea is explained, so we have another question done for series solution. Questions? So are we okay with 5.2? Yeah, okay. Alright, so again, if you want more practice, do few more textbook questions. They're great. You're gonna like them. You'll enjoy them. Maybe not fully, but at least you will learn a lot of technique and you'll probably like them. Your notebook will appreciate you too. So Sadia told me that she was writing a lot past few days, so that was good. Alright, so we're gonna move on to 5.3. 5.3 is another really fun topic. It's series solution near ordinary point, part 2. So 5.3 is a quicker way of getting the coefficients, but we're not going to really use it for this course. But still, it's good to see them, how we can compute these coefficients without getting a recurrence relation. So we also have alternative ways of doing these problems. But again, for this course, you need to know how to do recurrence relation. So you can think of 5.3 as an optional section. So if you like it, enjoy it. If you don't like it, it's okay, you'll learn. So 5.3. So this is series solutions near ordinary point, part 2. Okay, so I will just put this as optional. R/fun. This is also a fun way to get coefficients, but it's really optional because you really need to know 5.2. That's mandatory. So we're going to borrow the Taylor's expansion one more time. The formula we got previous section in 5.1 when we reviewed power series. So we know the following from Taylor's expansion, that you can express any function that's infinitely differentiable as an infinite sum. So we can express f of x as an infinite sum. We have the sum n from 0 to infinity, f to the nth derivative, evaluated at x naught over n factorial times x minus x naught to the n power, right? So if you look at this and the solution we assume, right, we set our solution form for near series solution near ordinary point is y equals the infinite sum n equals 0 to infinity an x minus x naught to the power n. Almost the same, right? Almost identical. So what can we do? We can kind of say, so it's like saying that this is our formula to get the coefficient an. So that's the connection we're trying to make. So we can use this, and so we can use Taylor's formula to compute the coefficients of our series solution. Okay, so an, it's going to be determined by this formula, f to the nth derivative, evaluated at x naught, dividing it by n factorial. So that's how we'll get the coefficient. So this is another way of getting the coefficient, a quicker way to get the coefficient. So it's a really nice method. But the downside of this method is that it will never give you the recurrence relation. So if the question asks you for recurrence relation, this is not useful. This is useful to get the solution, but not the recurrence relation. Okay, so just keep that in mind. So let me write that down for you as well. So remark. So this method will not provide recurrence relation. So that's the downside. You don't get the recurrence relation. But let's see how it is still useful, right? So the key idea is this magical formula right here. Well, what does this mean? So the way we're going to use this formula is if I'm looking for the, let's say I'm looking for a sub 2, right? So for example, if I want to find what is a sub 2, so we know a0 and a1. They're just themselves, right? a0, a1. What about a2? How would I use Taylor's formula to compute a sub 2? So if you think about it, this is just the second derivative of the function evaluated at x naught over 2 factorial. Do you see the connection? Right? And if I want a3, then we can say, oh, okay, that's just the third derivative evaluated at x naught over 3 factorial, and just keep going. So even if you want the 30th term of a solution, you know that's going to be a to the 29th, right? Because 30th term will be the a sub 29, f to the 29th derivative over 29 factorial. So you get the idea. You can compute any specific term you want. That's kind of cool. I thought that's very nice. Let me do an example so at least this idea explains. So here is an example to illustrate this. So suppose you want to find solution to the following differential equation. Y double prime plus sine of x times y prime plus cosine of x times y equals to 0, given y of 0 is a0 and y prime of 0 is a1, okay, and x naught is 0. So again, we're centering at 0, so it's just nice. Okay, so, well, we know that our solution is going to be a power series, so we have a0 plus a1x plus a2x squared plus a3x cubed, and so on, right? So let's get the coefficient using Taylor's expansion. So, well, a0 and a1, leave it as it is, but how do you compute a2? Well, we just said a2, it's going to be the second derivative over 2 factorial. So let's do that. Well, I have my equation in terms of second derivative. All I have to do is solve for second derivative. So if I take the given equation and solve for y double prime, so we have negative sine of x. So y is kind of like the f of x, right? So if you remember here, y is our f of x. We're just using y instead of f of x. The textbook uses phi. So if you follow the textbook, it's going to say phi to the nth derivative evaluated at x naught over n factorial. So same formula, just looks different, okay? So, alright, so having said that, let's come back to this. So I'm going to solve for y double prime by subtracting sine x y prime minus cosine x y. Okay, so that's going to give me a2, and then I have to divide by 2 factorial to get the actual a2. Well, let's evaluate this at x not equal to 0. Right? So what do we get? So we have hopefully you guys have it this way, right? We're plugging in 0 into the function. So someone said the answer, I didn't catch it. So this goes to 0. So y of 0 is 1. So, no, wait, hold on. Y of 0 is a0. And then cosine of 0 is 1. So we have negative a0. So that's y double prime, right? So we know that a2 is going to be y double prime, which is f, as we wrote down before, evaluated at x naught over 2 factorial. So our a2 is going to be negative a0 over 2 factorial. So that's going to be a sub 2. So you see how quickly you can get the coefficient without even worrying about what's the recurrence relation. But there's always downside to everything, so it's okay. So we found one of the coefficients. Let's go for a3. So I'll give you guys a few seconds to come up with that. Okay, so for a3, we need the third derivative. So I'm going to take this equation I have right here that I already solved for y double prime. I'm just going to take another derivative because that will give me the third derivative of this. So you just keep working with your original equation that was given to you. So the third derivative, it's going to be, we have to use product rule. So we have negative cosine of x y prime minus sine x times y double prime. And then the second function, we also do product rule. So we have positive sine of x times y, and then minus cosine of x times y prime. So that's the expression for the third derivative, which will give us the third a3, but we have to divide by the third factorial. And then we want to evaluate this at x not equal to 0. So we have negative cosine of 0 and y prime at 0 minus sine of 0, y double prime at 0 plus sine of 0 times y at 0 minus cosine of 0 times y prime at 0. So everything that involves sine, they're all 0. So this is 0 and this is 0. So first and the last will survive. So we have, what do we have? We have cosine of 0, that's 1. So we have negative 1 times, what's y prime of 0? What was that? A1. And then the last term, again, that's cosine of 0 is 1, y prime of 0, that's A1. So what we really have is negative 2A1. So that's corresponding to y third derivative. So therefore, we say that A3 is going to be the y third derivative evaluated at x naught over 3 factorial. So in our case, we're going to have negative 2A1 over 3 factorial. That's the coefficient for A3. So let's write out the solution to this. So, and then you can go for the fourth derivative and just keep repeating the same thing. But I think the idea is explained. So our solution is going to be A0 plus A1 x plus A2 x squared, one more term, A3 x cubed, and so on. And now let's plug this in. So y is equal to A0 plus A1 x plus A2. We found it to be negative A0 over 2 factorial. So A2 is going to be negative A0 over 2 factorial, which is 2. I can just write that. And then A3, we found it to be negative 2 over 3 factorial A1 x cubed, and so on. And then if you want to group them by A0 and A1, you can also do that. But I will stop right here and let me know if you guys have questions. Yep.
Let's say they ask for the recursion formula, right?
Mm-hmm.
Do the cosine and sine, right? We would solve it in like section 5.2, right? Wouldn't we multiply the series for cosine and sine with it?
Yep, that would be crazy.
I know.
Yeah, so we wouldn't have a coefficient like sine or cosine if we want you to find recurrence relation. It will be polynomials, plain polynomials. Yeah, yeah. All right. So yeah, there you go. You have another way you can also check your work, right? I would say use this method to check you have the right coefficient. Go through the long process in 5.2 and use this method as a verifying tool. So it's nice to have tools. All right. So any questions on this? Okay. So if there are no more questions, moving on to the next section. So the next section we're going to cover is going to be 5.4. So this is 5.4 Euler equations. Okay, and regular singular point. Okay. So this is 5.4. Now if you want to do 3.4, that's also useful. So those problems that you couldn't do from 3.4 before, where you label Euler equation, that's like a tiny portion of 3.4. You can also do them now after we finish 5.4 because they're related. So let's look at another type of equation. Okay. Now these equations are very special because they have a name. We call them Euler equation. Some textbook calls them Cauchy-Euler equation. So if you ever come across a different textbook of differential equations, you might see it as a name Cauchy-Euler, because both mathematicians kind of work on this topic. So let's recall from 3.4. So we didn't really see it. So for us, it's just going to be rewriting the general form of an nth order differential equation. Okay, so the general form of an nth order differential equation with function coefficients, okay? So it's going to be an x to the nth power, so that's a polynomial, and then y to the nth derivative. So y has the derivative where x is a polynomial, okay? So make sure you note the difference between the n on the x and the n on the y is the derivative, plus a sub n minus 1 x to the n minus 1 power and y to the n minus 1 derivative, plus all the way up to, say, a1 x y to the first derivative plus a0 x to the 0, so that's just 1, times y to the no derivative is equal to 0. So sort of like the nth order differential equations, function coefficients, okay? So the coefficients are not real numbers, they're functions, function of real numbers. Now, what is an Euler equation? So we're going to be only dealing with second order Euler equation. So it's going to have a very specific form. So second order Euler equation. So the second order Euler equation has the form x squared y double prime plus, say, beta x plus y prime plus gamma times y equals to 0. Okay, so the coefficient of the second derivative in front of x squared is going to be 1. Let's assume that's 1. So always assume this is 1. And this is what we call a standard form. So this would be the standard form of Euler equation. Okay, so now what do we want? Well, the idea is simple. We want solutions. How would the solution look like if we're dealing with this particular equation, okay? So if you look at it very carefully, all the coefficients in front of y, y prime, y double prime, it's kind of like a quadratic, right? You have x squared with the second derivative, you have x with the first derivative, you have constant with the no derivative term. So it's sort of like a hidden quadratic, but with, of course, differential equation. So in this case, we're assuming beta and gamma are constants. Okay, so they're just real numbers. So we want to know the solution form to this. So what is the solution form if we have an Euler equation? So here's what we're going to assume. We're going to assume that the solution looks like y equals absolute value of x to the r. Okay, so instead of the exponential to the r t, we're going to assume now it's x to the r. It makes sense because if you see the coefficient of these derivatives, they're all polynomials. So it would make sense to assume that the solution also look like a polynomial, like kind of a polynomial, x to some power r. So r is just any real number. Now, this can be written in two different ways. So if x is positive, then you can just say the solution looks like y equals x to the r. And if x is negative, then you want to bring in those absolute value. So you would say absolute value of x to the r. But in general, I'm just going to put absolute value of x to the r. If it's not mentioned in the question, are we assuming x is positive? Okay. Now, so before we talk about regular singular points or any sort of singular points, we want to know how to solve these equations, Euler equations. And then we can talk about series solutions about these kind of equations. So if I assume that's the solution form, well, let's see, what do we get if we plug these in, right? So I'm going to work with the first case. Just assume that x is bigger than 0. So we're going to say, okay, y is equal to x to the r. That means I can compute its first derivative and second derivative and plug it into the standard form. So let's see how that looks like. So we have r times x to the r minus 1. That's the first derivative. and the second derivative is r times r minus 1 x to the r minus 2. The usual, right? Take the derivative. And now let's substitute those into the standard form of Euler equation. So we have x squared. Now plug these into standard form. So let's see what we get. So we have x squared, y double prime. Well, that's going to be r times r minus 1 x to the r minus 2. And then plus we have beta x times y prime. That's going to be r times x to the r minus 1. And then the last term we have is gamma times y. So that's plus gamma times y. That's x to the r equals to 0. So we assume that's the solution form. We computed its derivative. Now plug everything into the given equation, which was the standard form of Euler equation. Well, now, what can we do? We can simplify a little, right? So if you notice, I can combine the exponents for these terms. I can combine the exponent for these, and then let's see how it looks like, right? So if I combine their exponents, I get r times r minus 1 x to the, so the x to the 2 and x to the negative 2, they cancel out. You get x to the r. Plus the second term we have beta r, and then x and x to the r minus 1. If I combine those powers, I get x to the r plus gamma times x to the r equals to 0. Pretty nice, right? Well, now I can factor out what's in common, which is x to the r. So we have x to the r in common, and then we're left with r times r minus 1 from the first term, and the second term we have beta r plus gamma equals to 0. That's neat. It's a polynomial, right? So just like before, when we assume that the solution form for the constant coefficient was y equals e to the rt, you plug it into the differential equations, you took its derivative, and you saw that you get a characteristic equation, and that happens to be a polynomial, so we call it a characteristic polynomial. Here, we're not going to call it a characteristic polynomial, but it's a characteristic, but we're going to call this an indicial equation. So this equation right here, this is a polynomial, and we're going to call this indicial. So the reason this is called, well, one of the reasons that this is called indicial equation is because in 5.5, when we find series solution near regular singular point, you will see that you will need an indicial equation, which will be the characteristic of the Euler equation. So the two sections connect together later on. So for now, we're just going to introduce the name, but later on you'll see the connection. So now that we have an indicial equation, which is a polynomial, well, we have to break it down into 3 different cases, because a quadratic, so specifically this is a quadratic. A quadratic can have 3 different types of roots, right? You can have real distinct, you can have real repeated, or you can have complex. So 3 different ways you can represent the solution to this. So let's break it down. So 3 cases for the roots to the indicial equation. So the first case is nice. Well, they're all nice. So if R1 is not equal to R2, that means it's real distinct. Okay, so if that happens, well, how would the solution look like? Then the solution would have the form y equals, well, what are we assuming? Solution is x to the r, right? and if x is greater than 0, sorry, if x is less than 0, you put absolute value. So we're going to say the solution is the linear combination of x to the r1 plus x to the r2. So that would be c1 absolute value of x to the r1 plus c2 in absolute value x to the r2. So again, you're free to drop this absolute value if x is positive. Now what about the second case? If r1 is equal to r2, so that's real, repeated. Well, just like before, then our solution is going to be, so the first solution looks like c1 in absolute value x to the r1 plus, now how would the second independent solution look like? So here's the thing. So you'll have c2 ln of x times x to the r. So you're adding in, or you're multiplying this extra factor of ln of x to make your solution distinct from y1, right? Now if you remember from before, we would multiply by a t, right? T to make it different if the roots are real and repeated. Here you're plugging in ln of t, sorry, ln of x. Now where is this coming from? Well, you can show that the second solution, it gets multiplied by ln of x by reduction of order. So you can use reduction of order to verify. But if you trust me, this is right. Okay. The third case. I'm not verifying the second case. I think you can handle it. We have done enough question. You're up to the level where you're able to handle verifying things for yourself. Okay, so you can verify that on your own. Now the third case will be the complex roots, right? So if r1 and r2 are complex, so C stands for complex. So complex root. So that means we have r. So let's write r is equal to some sort of a plus bi. So just gonna write lowercase b, right? Plus and minus. Now we said previously it's okay to ignore the negative, right? Because the two solutions are just going to be combined using laws of exponents and some trig identities. So I'm going to drop the negative part, okay? But so let's see, how would the solution look like? Well, so this one I'll give you a little illustration, but number two you'll have to derive it for yourself. So if that's what we're assuming, then what do we have? Well, let's see. So we're saying that the solution is going to be x to the r. Well, if r is a complex number, so you have x to the a plus bi, right? So now what I'm going to do is I'm going to write this in a very funny way. I'm going to do e and then ln at the same time, x to the a plus bi. So you guys agree I didn't change the question, right? I just raised to a power and I exponentiate it. Okay, so well, now I can use laws of exponents. So that was the purpose of doing this, doing e and then ln at the same time. So now by using laws of exponent, the laws of logarithm, we have e to the power a plus bi times ln of x, right? One of the property of ln is to bring down the exponent. If it's on top, you can bring it next to ln. So that's the property. Now here I'm going to use laws of exponent. So let's see. So you have e to the a ln of x plus bi ln of x. And then again, using laws of exponent, I can separate these. So this is e to the a ln of x times e to the bi ln of x. Now, this is supposed to remind you of Euler identity. Do you guys remember that? Maybe? If you add e to the I theta, that's cosine theta plus I sine theta. Do you recall that? Yeah. So that's the one we're going to apply here to rewrite this. So you can think of your theta here is b and ln. So that's how it's going to look like. So this is equal to e to the a ln of x times, and then using Euler's identity, we have cosine. So I'm going to put parentheses. Cosine of b ln of x plus I sine of b ln of x, close parentheses. So that's the expansion of this piece right here, all of that using Euler's identity. So now let's write out our solution. So we were able to simplify. Now if the roots are complex, then the solution would have the following form. Y is equal to, so I'm going to rewrite it one more time. So this part right here, I'm going to bring the a as an exponent again. So you will have e and ln, they will cancel out. So you'll have x to the a times cosine b ln of x plus I sine of b ln of x. So I just resimplify that one because it doesn't really do much. If you have e and ln next to each other, you can cancel them out. So now we're ready to write down our solution if the roots are complex for Euler equation. So we have y is equal to, well, c1 x to the a cosine of b ln of x plus c2 x to the a sine of b ln of x. That's how the solution would look like. So yeah, so we have three different cases. So if the roots are real and complex, then the solution would have this form right here. And if the roots are real distinct, we have, I'm trying to put all of these in one box. So if real distinct, that's the solution form. If the roots are real and repeated, then that's the solution form. And the complex one we just derived. So these are the three different ways you can write down the solution to Euler equation. And once you have the initial equation, then you know what the roots look like, and we have the three different ways of expressing the solution. Any question on the derivation of this? So if there are no questions, let me start with an example. So let's compute the, so hopefully you have this written down. Let's see how we can do some problems. So suppose we want to find the general solution. So find the general solution. So suppose you have 2x squared y double prime plus 3x y prime minus y equals to 0. Assume x is greater than 0. Okay. So it's almost in Euler's form, right? In standard position. But the coefficient of x squared, which has the double prime, has to be 1, right? So what we can do, we can divide both sides by 2. So then we have the following. We have x squared y double prime plus 3 over 2x y prime minus minus 1 over 2y equals to 0. So from here, we know we're going to assume that the solution looks like y equals x to the r. So you can take its first derivative, second derivative, plug everything in, but we don't need to do all of that, right? We can just jump to this step right here, where we have the initial equation, and then from there we can find the roots to this initial equation. Does that make sense? Okay, so let me know if you guys need me to show work, but we'll be plugging that in, and then we'll have this initial equation, r times r minus 1 plus beta r plus gamma is equal to 0. If that's how the solution looks like, then this is the initial equation. So what is beta and what is gamma for this problem? Just the coefficient, right? And then gamma would be negative. Yeah, so you guys got it. Good. And now let's plug them in, right, and find the roots to this polynomial. So we have r times r minus 1 plus 3 over 2 r minus 1/2 equals to 0. And let's find the roots to this. So I'm going to go ahead and multiply both sides by 2. So the step that I took from here to here, that was not so necessary in this question. You could have left the 2 there, and then you would have the 2 right here. But you will see in the future that why it is important to have that coefficient to be 1. So that's why just get used to it from the beginning, even if you have to do one extra step. It's always good to have that coefficient to be 1. Well, now let's just remultiply, and that's not a big deal. We can handle that. So we have 2r times r minus 1 plus 3r minus 1 equals to 0. And then if I expand this, this is 2r squared minus 2r plus 3r, that's plus r minus 1 equals to 0. And now, this is a second degree polynomial, like we said. So, what are the roots to this initial equation? We can try to factor, right? So maybe 2r and r. And then minus 1 and plus 1. Right? Yeah, I think that's correct. Well, so we have our root. So we can say r1 is equal to 1/2 and r2 is equal to negative 1. So we have two distinct roots. So we're in case 1. So if case 1 says, if the roots are not equal, they're distinct, then the solution is the linear combination of x to the r1 plus x to the r2. So our solution to this problem is going to be y equals c1 x to the 1/2 plus c2 x to the negative 1. That would be the solution to this Euler equation. Any questions? So these are all the steps we took. So you can see that once you assume this is the solution form, you can just jump to this part, which is the initial equation, and then from there identify your beta and gamma, plug them in, start factoring, find the roots, write out the solution. These are the steps you would take if you're solving an Euler equation. Okay, let's do another one. So same idea, find the general solution. Now for this one, I want to work on this problem. So let's do x squared times y double prime minus 3x y prime plus 4y equals to 0. So I'll give you guys a minute. See if you can come up with the general solution to this. Okay, so let's check this out, right? So it's in standard form of an Euler equation, right? You have y double prime with x squared, you have y prime with x term, and you have y with the constant term. Exactly in the Euler form we want. So let's write out its initial equation. So we're going to assume that so maybe I should use different color, right? I have so many options. I'm gonna go with green. Alright, so we're going to assume that the solution looks like y equals. So for safety, should we consider safety? Okay, fine. X to the r in absolute value. I didn't put down x is greater than 0, so let's put the absolute values there. So if that's the solution, you do the work and then you get to the initial equation. We have r times r minus 1 plus beta times r plus gamma equals to 0. So what is beta and what is gamma? Okay, let's plug them in. So that means we have r times r minus 1 minus 3r plus 4 equals to 0. And then it's a polynomial. We can find roots to this. We get r squared minus r, and then minus 3, that's minus 4r plus 4 equals to 0. And this can also be factored. I can factor this into r minus 2 all square equals to 0. So you see it has a repeated root, real. So we have r1 is equal to r2, just 2, so it's repeated. Okay, so let's write out the solution. So we know the solution is going to be x to the r1 plus x to the r2 times ln of x. Okay, so our solution is going to be y equals c1 x to the in absolute value 2 plus c2 x to the 2 times ln of x. That's the solution. Now if you want to write this fancier way, you can factor out x to the 2, so or we have y is equal to x to the 2 times c1 plus c2 ln of x in absolute value. Or you can write it this way, so not a big deal which way you write it. You can factor out the common term or you can leave it in there. Not a big deal. So any questions on this one? Alright, so if there are no questions, moving on to the next one. So, well, we haven't seen complex roots, right? So let's do one with complex root. So again, find the general solution for the following. So say you have x squared times y double prime plus x times y prime plus y. I think this has complex root. Yeah. Okay, so again, it's in Euler's form, right? It has x squared with y double prime. It has x with y prime and the constant with y. So it's in a good shape. So we can go ahead and classify its solution. So we know the solution will look like y equals x to the r. Take its first and second derivative, plug it in, and you'll get the initial equation, which will be r times r minus 1 plus beta r plus gamma equals to 0. And then we plug in beta and gamma. So what's beta and what's gamma? So beta is 1, gamma is also 1. So if I plug those in, we have r squared. Well, let me show more steps. R minus 1, r times r minus 1, plus r plus 1 equals to 0. So we get r squared plus 1 equals to 0. Okay, not so bad. So we have complex roots. R is equal to plus and minus I. So if I were to write this in a plus bi, so we know a is 0 and b is going to be 1. So now let's write out our solution to this. So our solution was, we said it's going to be x to the a. Well, a is 0 in this case, so x to the 0 term will disappear. So you're just going to have c1 cosine of b ln of x. B is 1, so 1 ln of x, plus c2 sine of 1 ln of x. So this would be the solution to this particular problem. So you get to see one of each. You get to see distinct real, repeated real, and complex. Any questions on any of these different scenarios? Okay, let's do one more. Let's do, let me see. So here's another one. So you can find the solution. So say you have x times y double prime plus y equals to 0. So is this an Euler equation? Well, is it in the form? So in order for it to be an Euler equation, we want this form. We want x squared y double prime plus beta x plus y prime plus gamma of y equals to 0. We want that because that's what an Euler's form is in standard form. Does it look like that? How do we make it into an Euler's form? So we want x squared term to appear with y double prime. How do we do that? Right? What do you guys think? How do we make y squared to have x squared on the front?
Multiply everything by x.
Yeah, right? Just multiply it by x, and that will do the job. That will put this in a standard form of Euler equation. And we want that so that we know how to identify what beta is, what gamma is, so we can find its initial equation and find its roots, write out the solution. So if I do that, we have x squared y double prime plus xy equals to 0. Now does it look like in the form that we want? Yeah, right? Check. Okay, well now let's identify what is beta and what is gamma. What do you guys think? So, anyone? So we have 5 minutes. Let's hurry up with this question. Yeah, right? Because we don't have this term, so beta is 0. What about gamma?
Just x.
Well, do we have this term on our? Well, do we have this term appearing in our equation, y with the constant. Yeah, so it has to be in the exact same form. If it contains extra term, you ignore those. Those are just not the coefficient we want. So if these coefficients are 0, so our initial equation is just going to be r times r minus 1 equals 0. And that gives you r equals 0 and r equals 1. So you have two distinct real roots. So our solution is going to be y equals c1 x to the 0, that's 1, plus c2 x to the 1. So that would be the solution to this. So classifying it as an Euler equation in the correct form is very important for this section. So I didn't get to finish 5.4. We have to talk about regular singular points, so that's going to be next time. Any questions on this? Are you guys okay? Okay, so I will take that as a yes. Thank you. All right, so we're done for today. So we're going to take a quiz at 7:30. So you still have 3 more minutes. Take a break,